The world stands on the brink of a technological revolution. This revolution is driven by quantum computing. Quantum computing is not just an incremental improvement, it is a fundamental shift in how we understand and harness computation. Imagine a future where complex problems once considered impossible to solve become solvable. This is the promise of quantum computing. At the heart of quantum computing lies the qubit, a fundamental unit that holds the key to the next revolution in technology. Qubits are the quantum equivalent of bits in classical computing, but they are far more powerful and versatile. Classical bits can be either 0 or 1, representing a binary state that forms the basis of all classical computation. Qubits, however, leverage the strangeness of quantum mechanics to achieve something extraordinary. They can exist in a superposition, being both 0 and 1 simultaneously, a state that defies classical logic. This unique property allows quantum computers to explore many possibilities at once, vastly increasing their computational power. It's like flipping a coin that can land on heads, tails, or both at the same time, creating a new realm of computational possibilities. This parallel processing power gives quantum computers their immense computational advantage, enabling them to solve problems that are currently intractable for classical computers. Another key concept in quantum computing is entanglement, a phenomenon that Einstein famously referred to as spooky action at a distance. Entanglement links qubits in a way that their fates are intertwined, meaning the state of one qubit directly affects the state of another, no matter the distance between them. Measuring the state of one entangled qubit instantly reveals the state of the other, no matter how far apart they are, a property that is crucial for quantum communication and cryptography. This interconnectedness is crucial for performing complex calculations and simulations, making quantum computers a powerful tool for scientific research, optimization problems, and beyond. IBM has been a pioneer in quantum computing. Their journey began with the IBM Quantum Experience in 2016. This was a cloud-based platform that gave the public access to a 5-qubit quantum computer. This initiative democratized access to quantum computing, fostering a global community of researchers and developers. IBM continued to innovate, pushing the boundaries of qubit count and performance. They introduced a series of increasingly powerful quantum chips. These include Falcon, Hummingbird, Eagle, and Osprey. Each iteration brought improvements in qubit coherence, gate fidelity, and scalability. IBM's latest quantum processors, Heron R2 and Condor, represent significant milestones. Heron R2, with 156 qubits, focuses on improving gate fidelity and reducing noise. It incorporates advanced error mitigation techniques, paving the way for more reliable quantum computations. Condor, unveiled in December 2023, is a testament to IBM's ambition. It boasts an astounding 1,121 qubits. This massive qubit count is achieved through a novel chip architecture and advanced fabrication techniques. Condor utilizes cross-resonance gates, known for their simplicity and noise resilience. These advancements underscore IBM's commitment to achieving quantum utility. They aim to make quantum computing practical for real-world applications in the near term. Section 5. Google's Willow, a new era of quantum supremacy. In the rapidly evolving world of quantum computing, Google has positioned itself as a formidable contender. Their advancements are not just incremental but revolutionary, pushing the boundaries of what we thought was possible. Google has also emerged as a major player in the quantum computing race. Their commitment to innovation and excellence is evident in their state-of-the-art facilities and the brilliant minds they have attracted to their team. Their latest quantum processor, Willow, has made headlines. This processor is not just another step forward, it represents a significant leap in quantum technology. Willow, with 105 qubits, might seem less impressive than IBM's Condor in terms of qubit count. However, the number of qubits is not the only measure of a quantum processor's capability. However, it possesses a different kind of power. The true strength of Willow lies in its ability to perform computations with unprecedented speed and accuracy. Willow has demonstrated remarkable speed and precision in specific tasks. This processor has been designed to tackle complex problems that were previously thought to be unsolvable. It performed a complex computation in under 5 minutes, a feat that would take a classical supercomputer billions of years. This is not just a theoretical achievement, it has practical implications for fields ranging from cryptography to material science. This achievement highlights the potential of quantum computers to outperform classical computers for certain problem types. The implications of this are vast, potentially revolutionizing industries and scientific research. One of Willow's key innovations is its improved qubit excitation retention. This advancement addresses one of the most significant challenges in quantum computing. This means the qubits can maintain their quantum states for a longer duration, reducing errors and improving computational accuracy. As a result, Willow is not just faster but also more reliable, paving the way for more practical and widespread applications of quantum computing technology. Section 6. Comparing quantum giants IBM versus Google. In the rapidly evolving field of quantum computing, two names stand out prominently: IBM and Google. Both companies are at the forefront of this technological revolution, but their strategies and goals differ significantly. IBM and Google, while both leaders in quantum computing, have adopted different approaches. IBM has a long history in computing and has been investing heavily in quantum research for years. IBM focuses on building general-purpose quantum computers. Their strategy revolves around creating versatile machines that can handle a variety of tasks. They emphasize incremental improvements in qubit count, gate fidelity, and error mitigation. This methodical approach aims to steadily enhance the performance and reliability of their quantum systems. Their goal is to make quantum computing accessible for a wide range of applications. From pharmaceuticals to finance, IBM envisions a future where quantum computers solve complex problems across various industries. Google, on the other hand, is known for its focus on achieving quantum supremacy. This term refers to the point where quantum computers can perform tasks that are impossible for classical computers. They aim to demonstrate that quantum computers can outperform classical computers for specific tasks. Google's approach is more about showcasing the raw power and potential of quantum computing. Their approach is characterized by a pursuit of speed and precision, even with a smaller qubit count. Google believes that achieving quantum supremacy will pave the way for future advancements. Both strategies have their merits. IBM's methodical and inclusive approach contrasts with Google's ambitious and focused strategy. IBM's approach fosters a broader quantum ecosystem, while Google's pushes the boundaries of what's possible. Together, these two giants are driving the future of quantum computing, each in their unique way. Section 7. Quantum Horizons, Applications of the Future. The potential applications of quantum computing are vast and transformative. In medicine, quantum simulations could revolutionize drug discovery. They could enable the development of personalized treatments tailored to an individual's genetic makeup. In materials science, quantum computers could help design new materials with enhanced properties. These could range from super-efficient solar cells to lightweight and durable alloys for aerospace applications. Quantum computing could also revolutionize artificial intelligence. It could lead to the development of more powerful and efficient machine learning algorithms. These algorithms could accelerate advancements in fields such as image recognition, natural language processing, and autonomous systems. Section 8. Ethical Considerations Navigating the Quantum Frontier. The immense power of quantum computing also raises ethical considerations. The ability to break current encryption methods poses a significant threat to data security. This necessitates the development of quantum-resistant encryption algorithms to protect sensitive information. Another concern is the potential for bias in quantum algorithms. If the data used to train these algorithms is biased, it could lead to unfair or discriminatory outcomes. It is crucial to ensure that quantum computing is developed and used responsibly, addressing ethical considerations from the outset. Section 9. The Quantum Future. A tapestry of possibilities. The quantum future is brimming with possibilities. As quantum computers become more powerful and accessible, they have the potential to reshape industries, accelerate scientific discovery, and address some of humanity's most pressing challenges. The journey towards practical quantum computing is still ongoing. Challenges remain in improving qubit coherence, reducing error rates, and developing scalable quantum architectures. However, the rapid pace of progress in recent years suggests that the quantum future is closer than we think. The quantum revolution is not just about technological advancement, it is about expanding the horizons of human ingenuity and unlocking a new era of possibilities.